Hello everyone. Thanks for your participation in this session. In this session, I will be talking about our paper called Automatic Lyrics Transcription using Dilated Convolutional Neural Networks with Self-Attention. I am Emir Demirel, the first author of this paper, and this research is held in partnership with Doremir Music Research AB from Sweden and Queen Mary University of London from the United Kingdom. This research is a part of the Music Information Processing Frontiers project, which is a transnational, cross-sectoral, and multidisciplinary training network funded by the European Union under the Mary Skłodowska-Curie Grant Agreement. Here is the content of this talk. First, we will introduce our research topic. Then, we will briefly mention the literature in this research field. We will provide the details of our system. Then we will go through the results that we have obtained. Finally, we will finish with the future steps to achieve a better lyrics transcription system. So what exactly is automatic lyrics transcription? Well, this task can be seen as automatic speech recognition in the singing domain. In other words, it is the process of translating the linguistic content in the singing voice into text. Mathematically speaking, this task can be perceived as finding the most probable word sequence given the acoustic observations. Let me go through the literature of this research field. The bar chart on the left-hand side shows the performance of the existing lyrics transcription systems in research in terms of the word error rate. Compared to the state of the art in speech recognition, the performance of the lyrics transcription systems are much poorer due to few factors. For instance, the acoustic properties such as pitch, the dynamics, and the timbre have higher variance compared to speech. Further, the data resource in singing voice are much limited compared to that of speech. Therefore, our research is motivated by bridging the gap between the performances of the speech recognition and the lyrics transcription systems. In our system, we have employed the hybrid speech recognition approach. In this approach, the acoustic, the pronunciation, and the language properties of the speech, and in our case singing, voice signals, are modeled separately, which makes the overall system more adjustable and interpretable. Moreover, previous research showed that in the presence of limited data resource, hybrid speech recognition approaches outperform the end-to-end systems. Therefore, we employ this approach in our system. Let me go through some of the details of our system that we presented in this paper. Please note that in this work, we have focused on the acoustic and the language models of the lyrics transcription system. The purpose of the acoustic model in hybrid speech recognition approach is to learn the posterior probabilities of phonemes. In the state-of-the-art systems, this is done via training neural networks. In our system, we have trained our neural networks using the 40-dimensionality feature banks and 100-dimensionality I-vectors to achieve singular adaptive training. We have employed sequence discriminative training method based on the maximum mutual information criteria, which is the equation that you can see in the slide on the top right. The goal of this criteria is to maximize the shared information between the reference and the target sequences. Sequence discriminative training approaches are highly prone to overfitting. For that reason, it needs high amount of regularization. In our system, we are using a number of regularization methods, including the cross entropy, L2, and leaky HMM regularization methods. To further alleviate the risk of overfitting, we have also applied dropout after each layer in our neural network architecture. To achieve further performance gain, we have also applied data augmentation based on speed perturbation with the factors of 0.9 and 1.1. Here is the neural network architecture we have presented in our paper, which consists of three major components. In the backend, as feature extractors, we have used convolutional layers. After the convolutional layers, we use a stack of time delay neural networks. The reason why we have chosen time delay neural networks is due to their capability of modeling long-term context dependencies, and unlike RNN, they are parallelizable. To provide more robust and lower dimensionality features for the time delay layers, we have applied subsampling with the factor of 2 after the third, fifth, and sixth convolutional layers. After the time delay layers, we added a time-restricted self-attention layer just before the final classification layer. In our experiments, we have tested different language models. We have iterated over 3 and 4 grams that are trained over the maximum entropy criteria using the SRILM language model toolkit. To achieve better performance, we applied lattice rescoring with the pruned RNN-LM method. For training the language model, we have used data from different resources. First, we have used the lyrics of all the songs in the DAMP repository. In addition to that, we have used all of the songs from all of the artists in the Billboard The Hot 100 chart between the years of 2015 and 2018. The resulted training corpora for the language model has near 8 million words, over 1 million sentences, covering more than 4,000 songs. Note that each data point here is a lyrical line, which can be interpreted as a sentence. Let's go through the results. In this table you see in the slide, we show the performances of different language models. It can be seen that 4-gram language models are consistently outperforming the 3-gram language models. Rescoring lattices with RNN-LM also shows a notable improvement in the word error rate. Let's go through the acoustic model and the in-depth self-attention analysis. In this slide, we provide the illustration of the weight vectors in the self-attention layer. In our work, we aim to fine-tune the hyperparameters of the self-attention layer. The figures A, B, C, D show the iterations over the number of heads. They show that the more number of heads that we include in our self-attention layer, the more uniform distribution we obtain over the context bins. The figures E, F, G, and H are the iterations over the context in the self-attention layer. It can be seen that the more we increase the context in the self-attention layer, the less weights are assigned to the context bins surrounding the centering bin. We have also illustrated the training and validation losses of our neural network architectures. It can be seen that including self-attention layer results in lower loss in training and validation. Further, increasing the context also results in lower loss. However, increasing the context, similar to increasing to the number of heads, results in higher trainable parameters. For the number of heads, at each iteration, the trainable parameters increase in the orders of magnitude. And for the context, the trainable parameters increase in the orders of hundreds of thousands, which make the training more difficult and learning slower. In this slide, we show the word error rates of our iterations over the self-attention layers hyperparameters. We obtain the best result using 15 number of heads and the context, 15 context bins from the left and 6 context bins from the right. With the best parameter setting, we achieve around 15% of word error rate, which sets the state of the art in automatic lyrics transcription that shows 5% absolute and 33% relative improvement compared to the previous best system. I would like to finally mention one more aspect of the self-attention and the effect of language models in the lyrics transcription systems. In this slide, we show that the lattices resulted from the decoding procedure. On the left-hand side, we see that the lattices from the dilated convolutional neural network without the self-attention and without RNN-LM rescoring. It can be seen that the lattice structure is quite complex. However, when we add the self-attention in the acoustic model, the lattice structure gets much simplified, which results in a higher performance and a performance boost in terms of time during the decoding procedure. Finally, when we applied lattice rescoring using RNN-LM, the number of paths in the lattice structure is reduced to only 1, which even improves the performance further. I would like to conclude our talk with the contributions that we provide through our research. We have provided a complete pipeline for the lyrics transcription systems from monophonic singing voice signals. We have presented a novel neural network architecture for constructing the acoustic model. We have provided an in-depth self-attention analysis and showed the state-of-the-art results in lyrics transcription. We are providing our research software as an open source framework for reproducibility and open science purposes. The future steps of this research can be categorized into 3. First, we need a better pronunciation modeling for the singing voice, as the pronunciation of uttered words change a lot due to the processes like melody construction and musical articulations. We need a better and a more specific language modeling for lyrics transcription. And obviously, we need more and more and cleaner data for training to achieve a better performance. If you'd like to check out the references in this presentation, now it's a good time to pause the video. If you have any questions or any interest regarding this research, please do not hesitate in contacting us through the email addresses that you see in this slide. Thanks for your attention and listening to this talk.